This problem, we have water flowing from a constant level tank at atmospheric pressure. It flows through a pipe that is 1 inch Schedule 40 and is 8 meters long, and that pipe is commercial steel pipe. It discharges to the atmosphere 4 meters below the level of the source of the tank, and we are asked to calculate the mass and volumetric flow rate, neglecting entrance and exit losses. And so we've got our properties here. We symbol our properties: nominal density of 1,000 kilograms per meter cubed, our viscosity. This is Schedule 40 pipe, so the nominal diameter is 1, inner diameter is 1 inch, but it's really 1.049 inches, 8 meters. We look up a roughness for this pipe because we're going to need to include frictional losses through this pipe, and then of course we have our elevation chain. As far as our assumptions go, we are told that the level of the tank the level of the water in the tank is constant. So that means, of course, that we've got some feed that we're not showing, but we don't really care about. The pressure, this is open to the atmosphere, so the pressure at 1 is going to be 1 atmosphere. Also, it is discharging to atmospheric pressure, so pressure at position 2 is going to be atmospheric pressure. We're also told that we can neglect entrance losses or exit losses, and so this means that we don't have and fittings losses. So we don't have a loss factor for contraction in going from the tank to the pipe. We don't have any losses due to elbows, bends, or valves, and we don't have any kind of expansion loss in going from the pipe to atmosphere. The only thing that we're going to consider in this problem is just the frictional loss between the fluid and our system. So this is water. Again, one of the kind of inherent assumptions that we have is that this is going to be an incompressible fluid. We are saying that our density is constant, and that also means that it's a steady state. So because this level is constant, the flow rate through this pipe is constant and not changing with time. So the strategy, what we are asked to find is we're asked to find the flow rate. And so what that means is we need to find the velocity at position 2. So what we can do is we can apply the Bernoulli equation between position 1 and 2, and we will solve for U2 as our for our solution, and then from the linear velocity we can calculate a volumetric and a mass flow rate. So we look at our Bernoulli equation, our general form of our Bernoulli equation applied at position 1 and 2. We can start crossing out terms. Number 1, there's no head added, right? There's no pump in this system between 1 and 2. There's no head extracted, so this term goes to 0. Our pressure terms, P1 and P2 are atmospheric pressure. They're the same. So we can, and as well as the density is constant, so these pressure head terms go to 0. What about the velocity? Well, at position 1, our velocity is 0 because we are told this is not this level is not changing. So our water is not moving at all at position 1 with the linear velocity. At position 2, of course, we have U2, and that is what we are asked to solve. And so if we take these assumptions and we apply them to our Bernoulli equation, this is what we get. We are using Z2 as the datum, and so Z1 is going to be 4 meters. We have head loss due to friction, and that is going to have to equal the head, the velocity head at position 2. So we can substitute in our or we can look up our head loss due to friction. This formula is given to you in your reference or textbooks. And remember, we are using the Fanning friction factor. We're not using the Moody friction factor. And so we can write this equation, this Bernoulli equation here. And what you can see here is that our desired or our unknown, our single unknown, is going to be U2. All right. So we need to calculate U2. So we've got a quadratic formula that we need to deal with. However, what we also need to understand is that velocity is the U2, the velocity in our pipe is also buried in this fanning friction factor term. And so what we have to do is we have to look at that and figure out how we're going to solve it. So we can only calculate the fanning friction factor if we know the flow is laminar or turbulent. So remember, if it's laminar, it's just F is equal to 16 over the Reynolds number. If it's turbulent, it's equal to this big number. All right. And so the velocity here, we've got it in terms of the Reynolds number, but then what I've done is I've substituted it in the Reynolds number, and so this is our friction factor term. So what we need to do then is we need to take this equation for F, we need to substitute it in here, and then we can solve for U2. So if we do that, a little bit of algebra, or kind of a messy formula here, but this is what we get. And so I just used MathCAD to do this, just copied and pasted the equation for F in here. And so this is what we get. We get this equation, and what I've done is I moved everything over, of course, to the left side, because that's how it's going to work easier in MathCAD. We need to solve this equation for U2. This would be a real pain to do with pen and paper, but we can do this in MathCAD pretty easily. We use the root function where we guess a value of U2 of 5 meters per second, and then we use the root function in MathCAD where we take the root of this function, which has been set equal to 0, and we ask it to solve for U2, and our value is 3.05 meters per second. So that is our linear velocity through the pipe. We are asked to calculate the mass flow rate and the volumetric flow rate, and so we can do that by calculating the cross-sectional area in the pipe. You get that, and then we take that and we take the density, linear velocity, cross-sectional area. We get a mass flow rate of 1.7 kilograms per second. We can then take the linear velocity and cross-sectional area and get a volumetric flow rate of 1.7 liters per second, and that is because the density, of course, is 1 kilogram per liter, so we get the same numerical answer for that. Another thing that we should do is when we use this formula for the friction factor, we're assuming turbulent flow. I forgot to mention that, but I did mention that it was different for laminar flow. Since this is water, it's more often than not in process fluidics type of flows, we're going to be dealing with turbulent flow. So that was our first guess. But we need to check that. We need to check that assumption, and when we plug the value of our calculated value of U2 in here, we get a value of 91,000. So that was and that is definitely higher than 2,300, 2,000, 2,300, and so we can. That is a good assumption, and so these calculations are valid. Now the problem didn't ask us to do this, but I would just want to illustrate again the what happens if you include some fittings in here, and whether or not they're significant. So we were told that we didn't have to add any kind of frictional losses due to fittings. But what I want to do is to add the head losses due to the transitions from the tank to the pipe, so constriction. And then based on this, there has to be at least one bend or elbow. And so I want to do that. And so what we're going to do is we're going to add one contraction from the tank to the pipe and one elbow, and then one expansion where we're going from the pipe to, say, another tank. So another reason why I want to do this is to just illustrate that you have a choice in how you would approach this kind of problem. And so if we were to choose the velocity head approach for the frictional losses, it would be a little bit more difficult, because remember, we don't know the velocity U2 in this line, and so everything, it it would certainly be doable. It would just be and really it wouldn't be that difficult in MathCAD. But if you were doing this manually, it would be a lot more difficult. So to make things a little easier, what I think would be what I wanted to illustrate is that we have a choice. We could use velocity head, but let's use the equivalent length method, because velocity is in here, and we would also have to include the velocity head, but the equivalent length method should be a little easier. So if we do that, we can calculate, we look up, I should say, we look up the values for the equivalent lengths for the constrictions, for the 90-degree bend, and for the expansion, and you see we get an equivalent length head loss of 2.998, or about 3 meters. We add that to our loss for the pipe, and you see we get about 10.9 or 11 meters. If we go up here, we did not, if we go up here, let's see, we did not explicitly calculate the head loss. So anyway, we can't compare it directly, but this is our head loss due to the pipe plus the fittings. And so if we calculate the head loss due to the pipe, that's just going to be 8 meters, right? The equivalent length is going to be 8 meters. And so you can see that it is added about 37.5%. So the fittings would add quite a bit. So anyway, it's not insignificant. We can then plug this into our Bernoulli equation, where the total head loss is going to include the equivalent length, which is now 11 meters and not 8 meters. We're going to still assume that the flow is turbulent, right? We're still assume the flow is turbulent, and so we have our same equations for the fanning friction factor. We then take this and we use MathCAD to solve for U2, where again we had a guess of, we'll say 5 meters per second. We then use the root function. We use the root function for this, and we get a velocity of 2.6 meters per second. And to remind ourselves, what did we get above? We got a velocity of 3. We got a velocity of 3 meters per second. If we do our calculations for the volumetric flow rate and the mass flow rate, you see our mass flow rate is 1.4647 kilograms per second, or 1.47 liters per second. Notice that it was, without the frictional losses, it was 1.7. So as you can see here, is this significant? I think it is. It is somewhat significant. There are some significant differences when you neglect frictional fittings that are in your pipe, and you can see if you don't include those, you overestimate the mass flow rate. If you do include those, you will probably get a little bit more realistic calculations of flow rates in these systems. And again, I didn't mention this, but it's pretty obvious though that we need to check our assumption for turbulent flow, and we were quite safe with that assumption. We do have turbulent flow. So again, frictional losses due to fittings can be significant and can have a significant effect in your process fluidic calculations. So be careful if you assume that they're 0.